probably your least favorite thing about stats is dealing with the confidence intervals and hypothesis testing. We're going to end with this. Now, a little positive note. See this little G here? This G? This is the last lesson you're going to have, seniors, from me all year. We're stretching it over 2 days, but it is still the last one. All right, so bear with me. Of all the things I've taught you this year, this is probably the most applicable. You'll probably see this. When I went to college, I had stats 3 times. Every time I got a degree, there was a stat component to it. For my master's, it was an educational stat. For my PhD, it was even more advanced educational stat. And I just want to tell you that confidence intervals are really, really easy. Would you take your fingers and go like this? Okay. Now, if you are thinking of a number line of 0% to 100%, a confidence interval is between your fingers. The mean that exists is going to have a certain percentage of certainty that real mean is in there. So let's say that, I can always use candy bars for an example. You buy a candy bar. Are all candy bars created equally? No, but they have a mean, the weight that they put on the wrapper. But if you mass that candy bar, it probably wouldn't necessarily be that. Most machines are accurate to a certain amount. So what they would say is with a certain amount of confidence, that mean of let's say it's 1.3 grams, we have a 95% confidence that candy bar is somewhere between, I'm just going to make this up, but 1.25 and 1.35 grams. So I give a 95% chance that is. Could you get one that isn't in there? Yeah, but more than likely you're going to have one that is in there. And so what we're usually interested in is take your fingers again. There's an accepted mean, and let's say it's 1.3, and that forms a confidence interval around it. If you get a candy bar, I'm going to give Marie a candy bar after class today, and she's going to mass it, and then she's going to see if that fits in there. Now, does it have to fit in there? No, we probably would expect it to if this is my interval. Now, can we narrow this interval? Absolutely. We can claim it to be anything we want. If it's 95, hold your fingers like this, if it's 95% confidence, what do you think happens if we say 99%? It has to get wider, right? Because you got to catch more. How about 90%? I think it's closer, right? And so what we're going to do is we're going to connect it 2 ways. And the easiest thing to get through to you right away is that if you, and do you see these words, central limit? Would you put a box around that? If you have enough, as n goes to infinity, as you get more and more items, this curve becomes normal-like. And then where the mean is 0 and the standard deviation is 1 for what we call a z-score. So the z, you're going to get the more values that you use, you're going to get close to that normal distribution. So that's one thing that we're going to use. And most of the time we use the normal, but some people say, well, how do I know whether to use a z-score or a t-score? And I want you to write this down right now. If you know your standard deviation or your variance, if you know sigma, we're going to use the z-score. If we don't know sigma or the variance sigma squared, we're going to use the t-test. And I like to throw that out right away because it's not that hard. If they give you sigma, you're going to use the z normal distribution. If they don't, then you're going to use the t-test. And I'll teach you how to do that. It's not that bad. All right, so let's see. What else is easy? Oh, this is easy. expected value is mu. That's what you expect it to be. No difference from what we just did. The variance, however, because we're looking at a sample, not a population, this relationship of variance is going to be sigma squared over n. And this is for the z, right? Z distribution. And this is the variance. How do we get standard deviation? What do you do? Square root of that. So it's going to be sigma over square root of n. Have I done anything real complicated yet? No. Okay. So now is where the words just start to flood in and drive us crazy. But think of, if you know what sigma is, we're going to use this distribution. Variance is sigma squared over n. Now there's one more formula that we're going to use, and that is for the normal distribution. We're going to use this formula. Z is equal to the sample mean minus the actual mean over sigma. Okay? That's the normal distribution. This is the sample mean we're talking about, like Marie's candy bar. And this is the accepted mean. Now that's for a population. All we do for a sample, it's no biggie, just divide this by square root of n. Central limit theorem. I'm feeling good about this. This isn't bad, is it? So probably what we should do is deal with this confidence interval thing. So to deal with the confidence interval, we're going to say, well, if it's 95%, hold your fingers like this. 95% is between my two fingers. What's this finger area going to be? If the in-between is 95, what's this finger going to be? 2.5, and what's this one going to be? 2.5. So what I like to do when I see things like 95%, I like to draw a bell-shaped curve, and I like to cut it off here and here and say that this is 2.5%, 0.025, and this one is 0.025 or what is that, 975? Well, let me do it this way. This is the area. And this is going to get us to the location here and the location here. We need to know these areas here are 0.25, 0.025, 0.025, but this location, we're going to find the z-score. We want to find this thing. Have I lost it yet? Okay, so if I want to find this thing, there's something in your calculator called inverse norm, because we're using a normal distribution because we know the variance. And you're going to put in, no big deal, you're just going to put in that percent, 0.025. And can you get your calculators out? Tell me what that is. Inverse norm of 0.025. And then below it, I'm going to go inverse norm of 0.975. I want to see what that one is too. And when I do that, did anybody get this one? It's negative something. 1.599. I'm going to call it 1.96. What's the inverse normal of 0.975? Ha! 1.96. Great. Isn't that easy? So you do inverse norm to change a probability into a z-score, which we use in this formula here. And so now we're all ready to figure this out. We want to know what values of x are going to work out. So we're going to solve this. Z times sigma over the square root of n is equal to x bar minus mu. No biggie. All you're going to do there is you're going to go z times sigma over square root of n plus mu is going to be equal to x bar. And there you got it. All I did was solve that equation algebraically. Algebra is easy. Now, if we want this confidence interval that you just saw here, all that you have to do is go mu minus that and go mu plus that, and you've got it. That's the confidence interval. So we said back in this, did we get a problem here or not? But if you had like 20 of something, this would be 20. If they gave you sigma was 1.3, you'd get that. You'd use 95%. We got the z values. If you knew the mu's, you plug those in. And this is all there is to a confidence interval. And now go to, skip all this junk. We're going to do this tomorrow. Skip it all and go to, I'm going to do all that tomorrow. Yikes. Go to number 3. It says a sample of 42 patients, N is 42, from a drug rehabilitation program show a mean length and expected value, mu, of 38.2 days. Do they give us the standard deviation? Yep. Sigma is 4.7. So do we use a normal or a t test? Normal. We're going to use normal here. And then for tomorrow, you're just going to set up this 90% confidence interval. Everything's here that you need. Good luck. Have a great day.